Alright guys, in the previous course we learned that each process uses a portion of its memory for a stack, for a heap, and for a text section. The stack is used to store the local variables of the particular process, the text section is used to store the code itself, which are the binary instructions, and the heap stores everything else. Looking at the stack first, the stack is a contiguous chunk of memory that starts out unused. When the first function is called, let's call it main, its local variables are stored on the stack in a grouping called a frame. When the main function itself invokes another function, let's call it cat, the local variables of the cat are stored in another frame on top along with the size of the frame and the return address, the address to jump back to when execution returns from cat. Likewise, if cat calls another function, which let's say is called dog, the dog's local variables, the size of its frame, and the return address to cat are stored in another frame on top. Notice that as we add frames, we have to keep track of the top of the stack, because that's where we add a frame when the next function is called. Many CPUs, including x86 CPUs, have a specific register for storing this address, usually called the stack pointer. When a function returns, the frame size is used to adjust the stack pointer back down to the last frame and execution jumps back to the return address. So when dog returns, execution returns to cat, and the stack pointer will point to the top of cat's frame. Notice that we don't have to actually delete any frames because the space of frame occupies will simply get overwritten by subsequent frames as needed. Also notice that the first frame is special because the program ends when the first function returns, so the first frame doesn't need to store its size or any return address because there's nothing to return to. Now the diagram here suggests that the stack grows from the bottom, but in many cases the stack frames start at high memory addresses and grow downwards. This in fact is the case with x86 CPUs. This choice though is mostly arbitrary. The size of the stack space in some systems is kept track of with another pointer, usually called the stack boundary, kept in another CPU register. In CPUs with this register, when the stack pointer runs past the stack boundary, this triggers a hardware exception, and the exception handler may increase the stack space by moving the stack boundary. However, the exception handler may decide at some point that the stack has grown too large and may simply refuse and then instead simply terminate the process. Generally, the process's stack should only get so big, a megabyte or two at the high end. When stacks grow past this size, is generally a sign of an underlying programming error that should be corrected and not accommodated. The most common cause of an overly large stack is an overly large chain of recursive function calls. When the program exceeds its available stack space, the error is called a stack overflow, like the question and answer website. When a stack overflow occurs on a PC, the OS usually terminates the errand process. And very simple computers, however, such as in embedded systems, the stack size is not necessarily monitored with a stack boundary. And so when a program consumes more stack space than it should, the stack may poke into parts of memory used for other data or code, likely causing unpredictable bugs. The common arrangement in PCs is to store the stack at the top of the process's address space and the text, the code of the process, at the bottom. All the remaining space in between is available for the heap. Unlike the stack and text, however, no heap space exists when the process starts executing. Instead, the process must explicitly request chunks of heap storage from the OS with a system call. In the call, the process specifies what size of contiguous chunk it wants, but the OS decides where to locate these chunks in the address space, and the chunk locations are not necessarily adjacent. When a process is done with a chunk of heap, it should give the chunk back to the OS with a system call to deallocate. It is the responsibility of the OS to keep track of which portions of the address space are free for future locations, but notice that as the process allocates and deallocates chunks in memory, the memory space can become more and more fragmented, effectively shrinking the size of heap chunks which the OS can allocate because each chunk must be contiguous. Here, for example, the largest heap chunk which the OS could allocate is considerably smaller than the amount of free space remaining. Good allocation algorithms can minimize this fragmentation, but the problem can't be avoided entirely. This partly explains why you should deallocate chunks of heap when you no longer need them. By deallocating, you free up areas in the address space so that they can be allocated again later. The broader reason to deallocate, of course, is that your process might simply run out of address space at some point. Even if your process only needs a modest amount of heap memory at any one time, if your process runs long enough without properly deallocating heap memory, the process may eventually run out of address space, at which point new allocations will fail, likely requiring your process to terminate prematurely. So failing to properly deallocate a needed heap memory is generally regarded as a bug called a memory leak, because the memory available to your program effectively becomes smaller over time. Now here you might ask, if the RAM memory starts from this address and ends here, how is it possible that each process, let's say process A, B and C, share the same set of boundaries? Well, the final address might differ from process to process, depending on how much size it uses. But the starting address, which is 0, is the same for each process. If address 0 is the starting address for each process, that would cause a conflict between processes, right? One process will basically overwrite each other, which is something that we don't want. In the next course, let's see in more detail what is the trick behind this.